I'm handing out right now is the midterm from last year. And the idea of this is to use this as a study aid for the midterm. Because what I'm assuming is that most of you guys have probably not taken an exam like this in a little while, you know, for the most part, probably not, maybe not everybody. And I'm also assuming that this is probably the first graduate level physics course you guys have had, for most of you. So a lot of what this midterm is going to be about is going to be on not just being able to answer the questions, but also on developing a strategy and knowing how to take graduate level physics exams. So with so for what I handed you, you can use the midterm I'm handing in two ways. One, you can use it as sort of a model of what kind of problems are going to be on the test next week. And you can see it's going to be 4 problems. You're going to have maybe something like at the bottom like this, where it's Cauchy, Riemann conditions. And there's also, you could use Schaum's outline, but otherwise no notes, no other books. And so if you can answer these questions given that within the time frame, then you're going to be good. Now, as far as strategy on answering the problems, there's 4 problems. Each one of these should take you, if you're prepared to do a half an hour apiece, roughly. If you can't answer the problem in half an hour, and you're spending more time on it than that, and you're neglecting the other problems, then you're in a really bad position. So what I usually recommend for students is, you look at how many problems you have. You keep in mind that this is graduate level physics course. That means partial credit is important, and you need to at least attempt every single problem. So I'd say you look at the problems, do the easiest one first. If you can't get that problem, like significant headway done with that problem in the first 15 minutes, move on to the next one. And then you can always go back and work on the other problems later on. But I'd say at least you should have attempted all of the problems. Ideally, you should be able to do all 4 problems in 2 hours, go back, check all your answers, and turn it in, and you should be out of here before 7 o'clock. So that's the way the test should work. Okay? So, and like I said, you're essentially just solving problems, which is something you guys have seen before. Are there any questions about how the exam is going to work, or anything, or how to approach it? So the plan is going to be today. What I would like to do is kind of go back and do a little review over what we've talked about for the first few weeks of class. And then after the review on Thursday, then that's going to be a time when you guys can ask any other questions you have over anything that's lingering or anything that's not clear, or the homework that's due next Tuesday. And then next Tuesday is going to be the exam where you're going to turn in the problem set that's outstanding right now. And then on the following Thursday, what I would like to do is spend that time talking about the exam and the solutions to the exam, as well as any questions you guys have about that homework. So hopefully I can get that homework and the exam graded by that Thursday class. So anyway, that's the goal of how I hope things work. And as you're studying for the exam, what I'm recommending is you look at the problem sets, both the one that's out right now and the ones that you've already been handed back. You look at similar type problems between the ones that I have on the sample exam and the ones that you've done on your homework. You look at any other sources you could think of. You can go back and review the lectures some more, whatever you think will be appropriate. And remember that this the midterm exam is worth as much as all of your problem sets are going to be worth. It's 30% of your grade. So that means that even if you haven't done the greatest on the problem sets, you do well on the midterm, it counts just as much as all of those. Okay. All right. So, any other questions before we get started? All right. Yeah.
Sorry, Sean's calculator.
I don't think the calculator will do you much good, but if it makes you feel comfortable.
It helps.
Yeah. Yeah. I mean,
I think I should copy that one down.
oh, yeah. Everybody get a copy? So like I said, if you can, just be prepared to be able to handle these problems, and if you could do each one of these in about half an hour, you're probably going to be pretty good. The midterm you're going to get is probably not going to be too different from this. Okay, so, yeah. It is. That's fair game for this one, since that is one of the topics we're covering in the first half. I gave this as sort of an example, but yeah, there's going to be, it's fair game. Everything you've had a problem set over is fair game. What might happen, though, is that the complex variables could be rolled into another problem, like if you have to solve an integral, which happens to involve complex integration, and that could work. So I can't tell you 100% that there will be exactly one question on each one of these, but there's, these are all things that are fair. Any other questions? Okay. All right, so we're going to talk about the topics we're going to talk about today is ODEs, which was week 1. There's Infinite Series, which is week 2. There's Integration, week 3. Fourier Series and Transforms, week 4. And then Complex Variables. Which is last week. So these are the 5 topics that are possible for the exam. And so what I was planning to do was just kind of go, really quickly through these. I'm not going to go into as much detail as the lectures, obviously. And my notes on these are a little, they're not quite as good as some of my other notes, but just to kind of give you the flavor of what we're doing, and then to answer any questions you guys have. So the first topic, we talk about ODEs. And the basic idea here is that when you're solving the ODEs, the first thing you need to do is classify the ODE by order and degree. Because if it's a first order, first degree equation, it's a lot different than if it's a second order, first degree equation, or fifth order, first degree equation. And so the classification is going to determine your strategy, and the way you're going to work with the ODEs is you classify, and then based on that classification you develop a strategy, and then you have to implement that strategy, which means maybe going through different levels of kind of checklists. I haven't actually taken the time to make a flow chart on this, but this is the kind of thing you can develop a clear flow chart on how to solve. So for example, if it's first order, first degree, and this is going to be at least half of the differential equations that you'll run into are going to be first order, first degree. Then there's a well plot out way that you can go about solving it. The first is see if it's separable. Separable basically means algebraically you can separate the two variables if there's two. So if it's x and y, then you could have one integral which is a function of x and another integral is a function of y. And so that would be algebraically getting to the point where you have f of x dx equals g of y dy, where these are just some functions of only x and only y. Then what happens is, if this is only a function of x and this is only a function of y, these two both must be equal to constants. And so in this case, if they're separable, or you can separate them, then you can just integrate it and you're done. But this only works if we're talking about first order, first degree. And if it happens to fall in this category, then it's the easiest differential equation you could possibly get. Another thing you could do is you could test to see if it is exact. And to be exact, it basically, what happens is if you have a of xy dx plus b of xy dy equals, say, 0, then this is equivalent to saying partial u with respect to x dx plus partial u with respect to y dy is equal to du. Okay? There's a certain symmetry between that. If partial a with respect to y equals partial b with respect to x, and therefore a equals partial u with respect to x, and b is equal to partial u with respect to y. So for separable, it's just a matter of algebra and just seeing is the algebraic equation true. For exact, it means you're actually going to have to apply a certain test to your equation. And that test is going to be this thing right here. So if this works, then it's exact. And if it's exact, then then this is true. And then once you find this, all you have to do is you're basically solving for u. And so if it's exact, then you would integrate a with respect to x, and you integrate b with respect to y, and out pops your solution, whatever u is, which is a function of x and y. And when you do that, the only thing you have to be very careful about is that if you're integrating this with respect to x, and a is equal to partial u with respect to x, there could be a function of y only in here. So out pops whatever this integral is, plus something that is only a function of y. And out pops with this one something that's only a function of x. Okay? So the idea, it's a little bit more complicated when you do that, but in principle, it works. Another thing you can do is the integrating factor. And the integrating factor is you multiply your a dx plus b dy by some function of x and y, and you end up with something that is exact. And so for the integrating factor to work, what we found is that all the integrating factor problems we used were in this form. dy dx plus f of x y equals g of x. And so if you use this form, then your integrating factor is just a function of x, and it is the exponential of the integral of f of x dx. So what's happening here is you can essentially use this in order to solve for your integrating factor, and then once you have your integrating factor, you plug it into here and you have your exact function and you're done. And so I'd say this is your number 1 way to solve it. This is your number 2. This is your number 3. Okay? If all those fail, then you go to number 4. And your number 4 is a substitution. Now, substitution is good because the goal of the substitution is to get it to separable. And so if you could do this substitution and get it to something separable, then it's easy. If you can't get it to something separable, then you could try to do exact or the other, but it's harder to see. So that's why I'd say your goal is to get back to separable. And so when you're doing your substitution, that's basically where you might take v equals xy squared and dv equals y squared dx plus 2xy dy or something like that, and plug this into the equation with the idea that you're going to eliminate one of the other variables. Okay. And so when you do that, you are you're essentially changing the variables, and then you're doing a lot of algebra in order to get yourself back to a point where you're just rephrasing the problem. And the idea then is that every single first order, first degree ODE is going to have a solution, and that's the reason why we use it so much, is because every single one of those problems is guaranteed to have a solution, and going through one of these 4 methods is going to find that solution. Okay? So this is very systematic in how you go through it. Now, if you're talking about second order or second degree or higher. And we didn't really talk about second degree very much, but we did talk a lot about second order. And the reason why is because when you look at physics problems, and you look at the laws of physics, most of them are second order differential equations. Very few third order differential equations. So what's going to happen here is that if you can solve second order, then you're in pretty good shape for solving most physics problems. And if you come out with something that looks like this, then you're going to go with something a little bit different than the strategy we used before, because you can't separate these, and they're not exact in the same sense that they are for first order equations. Here, you would just use the initial guess method for most of these. And the initial guess is something like you assume that the solution is like y equals a to the xm, or y equals a e to the mx, something like that.
with the idea that you take this initial guess where it has these extra parameters in it, A and M, and you plug it back into the original differential equation and then solve for what these parameters need to be in order for the solution to work. And in doing that, you need to solve for both the complementary and particular solution. Where you actually need to know what both of those are in order to actually solve the problem. Because the problem is actually, the solution is actually going to be the sum of those two solutions. Where here, the complementary solution is going to be the one where it's a homogeneous equation. Effectively, there's no, outside of the derivative term, there's no functions of, outside of, like, say, if you have a function of y, which is a function of x, you don't have any other functions of x that don't relate to y. And that's homogeneous, and so therefore you use a complementary solution to that. And the particular solution, where that's where you're including the whole deal. And so you have to solve for both of those, and then you're done. So the difference here is that when you're doing just the first order, first degree, you can be very systematic about it. There's some creativity you might have to apply in doing the algebra in here, but otherwise it's, if one doesn't work, you move to the next one. And make sure that, you're really sure that this doesn't work before you move on to the next one. Because if it's separable, then it's just a matter of dividing through by a factor of x or y, and, then you can kind of blow it right there if you don't just go ahead and solve it. If it's second order or second degree, then the first thing you do is this initial guess. That's one way to solve it. If it's something more complicated where that doesn't really work, you can try a power series. And this is basically the brute force approach to solving it. This is where you assume that the solution is y equals C0 plus C1x plus C2 x squared, etc. And you have to solve for what these coefficients are. If you could do this enough, you're guaranteed to solve the differential equation because the power series is going to converge to some function. And it's just a matter of using your knowledge of infinite series in order to find what that function is. The problem with that is that you really have to be a computer in order to really get that done for a lot of terms. So, on the positive side, you're going to get a solution. On the negative side, it could take you 1,000 years. So, there's good and bad for everything. So, what I would say is, this is typically what you want to do. And also, we touched on this, but this is not part of the midterm, are going to be approximate solutions. And the thing is that unlike the first order, first degree ODEs, when you get to second order and higher, or second degree and higher, there's not necessarily a solution that you can find that is like a universally accepted, always working solution that you can just easily find. And that's where these approximate solutions come in. And sometimes, this is why we have a field of computational physics, and if we can actually solve these equations, which you just can't solve analytically. So, so for the purpose of the exam, what's most likely going to happen is it's either going to be first order and first degree, or maybe a second order first degree equation. Something like that where if you look at the practice exam I handed you guys, you could see that this is just a first order first degree equation to have them solve. Not a particularly simple one, but it was, one of those. All right, any questions on ODEs? I know we went over it in class. I don't think I had you solving any differential equation with power series. I know I solved some integrals in class with that, and I solved. I think I solved some differential equations in class. But you can go back and look at the notes. But basically, the way it works is that you take this power series and you take its derivatives, which are very easy to do, and you plug it back in a differential equation, and then look at like powers of x, and sort of use that to solve for the coefficients. So it's extremely tedious. All right. Any other questions on ODEs? All right. So moving on, let's talk about infinite series. So for infinite series, first off, there's the term convergence, which you should be very familiar with. And the basic idea here is if you take the limit as n goes to infinity, and you sum from n equals 1 to big N, then this is going to converge to some finite number. Now, most of the stuff that you're going to do in physics involving infinite series, you only really want to deal with converging series. So most of understanding convergence is really knowing whether or not you're going to get something finite or something infinite, if it's going to go up to infinite terms. So I'd say 90% of what you're dealing with are going to be converging series. So that's where we're going to mostly concentrate on. You can do convergence tests, which you've read about in the books, and there's a lot of different convergence tests you could do. Or you can, or you can kind of put limits if you're not going all the way to infinity. But mostly, for most of these, you're going to assume that they're going to converge to something. Now, what you want to do then is, assuming that you have a series that converges, most of these problems are going to involve figuring out what it converges to. Or it's going to involve taking a series that's known, taking a function that's known, turning it into an infinite series, doing the integral or solving the differential equation or whatever you're doing with it, and then bringing it back into an analytic form. And so you're using this sort of convergence from function to infinite series and back. So this is really the real goal of why we study the infinite series, is because you want to be able to use it in the infinite series form when it's convenient for you, and you want to be able to put it back into a functional form when that's convenient. Because like I said before, if you could put it in the infinite series form, then you could solve any differential equation you want, which is pretty powerful. So what's going to happen is the best way to actually determine the convergence of the series is going to be comparing it to known series that you know. And there are the familiar series we talked about, which are in the Shalom's outline. You can kind of look at those, and you can use some of those as you need to. But remember, saying, if I ask you, this is a series, and I want you to know what it converges to, and your answer is it converges to square root of 2 because that's what Schaum's outline says, that's not an acceptable answer. It needs to be, show me in detail why it comes out to that value.
It's like really only.
What?
It's like really only okay if we, like let's say the derivative, or take the derivative and then we get a Fourier series, then we can go integrate that.
Right. Yeah, I mean, if you're doing it something like that, then that makes sense. So if it's a familiar series are just that small set like e to the x, or sine and cosine, or inverse tangent, or 1 over 1 plus x, or something like that. So those are all familiar series, but also another thing that's important are the geometric series. And I think the geometric series is even more important than the familiar series because this familiar series, they're basically products of Taylor expansion for the most part. And you can get a lot of these from Taylor expanding something. You don't always have time to work out the Taylor expansion, but you get the idea. So, but the geometric series is something completely different where for a geometric series that you have something like the sum of a times r to the n, where you're summing from n equals 0 to infinity. And that series is going to converge to well, I shouldn't say infinity. I'm going to just call this capital N. So this series is going to converge to A times 1 minus R to the big N over 1 minus R to the little n. Or sorry, 1 minus R to the n, little n. And so the basic idea then is that you can know exactly what the series is because of the geometric series. And so if you can take your series and you can make it look like a geometric series by taking integrals or derivatives or putting in parameters or whatever to do that, then you could basically figure out what your series is. So the neat thing here, the thing I want you to take away from infinite series is that you can use a Taylor expansion I don't know why I want to put the L before the Y. And the Taylor expansion is going to take you from a function to an infinite series. And this allows you to find a lot of series. You can also do things like a Fourier series or something like that in order to do the same thing in some cases. But Taylor expansion does it for a lot of them. And then you can use other techniques like geometric series, integration, and all that other clever stuff to go back from a series to a function. So I'd say geometric series, recognizing a familiar series, integration, differentiation. All of these are going to be used to take you from a series to a function. And these are all just useful things to be able to do. And the idea being that this will help you as you're going through different solving physics problems to where you can think in terms of either the series or the function. And then I think there were some other things we talked about along the way, like the Bernoulli numbers, and I don't think I have to go into how do you do the transformation of the series of the Taylor expansion, do I? Because I think that was covered pretty well. And I don't want to just repeat the lectures too much. All right, the next thing we talked about was evaluation of integrals. Now, when we talked about evaluating integrals, there was basically two parts to this, and I call this evaluation of integrals Part A, and Part B being actually using complex variables, and doing contour integration, which is the real engine behind this stuff. But at one level, you can evaluate the integrals by doing things like changing variables. Where you need to solve an integral in order to solve a differential equation or a Fourier series or something like that. And so you see a solution that's similar in Shalom's outline, so you have to change the variables in your problem to look like the ones in Shalom's. And then when you do that, you can essentially translate the solution, and you're done. So that's kind of like the really cheap, dirty, low-level way of solving integrals. Because, and it's almost the equivalent of saying, hey, I found a solution to the integral. Here it is. Okay. And the reason why I don't have any specific problems on this anymore is because that's pretty much what you're doing for most of these. The other stuff you can do is you can differentiate or integrate with respect to parameters. And so when you differentiate or integrate with respect to a parameter, what that means is that you might have a parameter that you normally consider to be a constant, but you're going to take a derivative with respect to it, which is perfectly legal. And the reason why it works, for example, is I'm going to call this I of A, integral with respect to parameter A, or parameterized by A. And what's happening is there's an A on the exponential, but we really care about x as what we're integrating with respect to. So what's happening here, and I'll throw another x in here. So what's happening here is that I can take a derivative with respect to the parameter a of this integral, and this second integral here, we happen to already know the solution to it. And so what happens is that this works because of the fact that the integrals commute, the integrals and derivatives commute with each other when they're with respect to different parameters. So if I want to take a derivative with respect to a of this term inside the integral, and I'm not integrating with respect to a, I can do that. Or I could take a derivative with respect to lambda of this. And so I can move this derivative in and out of the integral, it doesn't matter. And so this is just now taking the derivative of the solution to this integral. And so I'm basically recycling a solution that I already know in order to find a new solution, which is somewhat related to it. And so this is pretty common. The thing that you have to keep in mind with both this and with the infinite series is that sometimes, in order for this to work, you have to kind of throw in a term like like this exponential term. Like this exponential term may not appear in the original integral, but we can assume that, well, what went on was that a was equal to 0. Okay? So we had to kind of use our imagination in order to put in the term which we might take a derivative with respect to the parameter. And we do this in the integral. We also do this in finding the infinite series. As you guys saw, like there was a bunch of infinite series where there was a value of 1, and you said it was actually x to the 17th power or something like that. And then you could differentiate with respect to that x, and you can reduce it to a geometric series. So, same thing here. So this is legal to just start putting in these parameters, but it's just, it's just not clear because you have to be creative enough to decide that that's what is the best thing to be done.
Sorry, where did the x go?
Oh, right here?
Yeah.
Oh, what we did was we said, well, this is equivalent to taking the derivative with respect to a of this equation. So it's almost like we integrated this with respect to a.
Oh.
Okay. Yeah. I know I kind of did it backwards, but it still works. So you can do derivatives, you can do integrals, however, I mean derivatives and an integral are just inverses of each other, so either way you want to do it. All right. The next thing we did was the use of symmetry we talked about. And the reason why we brought this up was mostly this became very useful when we talked about the Fourier series. If you're doing it in 3 dimensions, this is useful. And the basic idea here is that if you're going to integrate something, let's say this is parameterized by k, and you have a volume integral of 1 plus k dot r hat. This is equivalent to integrating dr from 0 to infinity, or r squared dr, and then integrating d theta, or d phi from 0 to 2 pi. And then instead of integrating d theta, we integrate d cosine theta from -1 to +1. And when we do that, we're kind of assuming that k happens to be aligned in spherical coordinates along the z-axis, in which case then k dot r is just going to be k cosine theta, and we integrate with respect to cosine theta, or something like that. So when we're doing this use of symmetry, all we're really doing is we're just saying that we can make our integral a lot simpler by orientating our coordinate system so that we have an easier integral to solve. Okay? And then the next thing is you need to know is the integration by parts, which I'm not going to go into a lot of detail with, but you remember this technique where you have essentially the integral of u dv, and you turn it into uv evaluated over whatever the limits are minus the integral of v du. And it's up to you to figure out what's u and what's v in order to make this work. So if you do this correctly, This is a valuable tool for solving a lot of integrals. It's something that, you've probably used so much in other calculus classes that you kind of forget about it. But this is just part of the point of this that week, was just to kind of remind you guys of some of these techniques for solving the integrals, because it's just such a fundamental skill for all the other problems that you need to solve. You're going to use this for solving the differential equations. In some cases, you're going to use this for infinite series. You're going to use it definitely for the Fourier series stuff. And then, possibly for the complex variables, but that's kind of more complementary to this than using it for it. All right. Any questions on integration? I'm thinking that this is the easiest topic.
What did you say about K dot R?
Oh, K dot R. The idea here is that K is orientated along the z-axis. So K is basically I'm orientating my coordinate system, so the vector K is going to be K sub z, and then I know that we have a R sub z equals, or R hat sub z equals cosine theta. And so that just makes the math easier. If we had orientated this along the x-axis, then we would have sine theta cosine theta, or sine theta, sine theta cosine phi instead. And then we'd have to have a harder integral to do, because we have to integrate with respect to phi and respect to theta. So it's one of these things that you'll see a lot in a lot of different texts, and people will use it, but they'll never explain it. And so this is just the one time where we actually explain it so that you know where it's coming from. All right. All right, so next up is complex variables. Sorry. Yeah. Yes, thank you. Fourier. Skipping ahead. Well, first we did Fourier Series, and then we did Fourier Transforms. And so the basic idea of the Fourier Series is that you have a function, like say of theta, where theta is periodic. It has the same value at 0 and at 2 pi. And so if you have a function like that, then the basic idea, and this sort of complements what we talked about with differential equations, is that you can look at the solution of this function as being equivalent to the sum of every single function that obeys the same boundary conditions. And it's just the only difference is that some are going to be more weighted than others. So in this case, since sine and cosine both have the same value at 0 and 2 pi, then we sum up a bunch of solutions involving cosine and a bunch of solutions involving sine. So you can see that this is a constant value, and then these are periodic, just like f of theta. So for all the different values of, so basically all you're really doing here is you're adjusting the value n, and no matter what n you put in here, as long as n is an integer, it's still going to obey these same boundary conditions. And when we talk about partial differential equations, we're going to kind of come back to this theme on this idea that every single solution you have which obeys those same boundary conditions is equally valid. And it's just a matter of which ones are weighted more and which ones are weighted less. So the only real challenge to this is finding the coefficients. And you could find the coefficients by just simply taking the integral from 0 to 2 pi of f of theta cosine of n theta. And I'm going to just divide by 1 over pi here. And then for bn, I'm going to have 1 over pi, integral from 0 to 2 pi, f of theta sine of n theta. And we went over exactly where these came from in class. So the real thing with the Fourier series is basically saying that we know we have a periodic function, but it has to be periodic for this to work. And then once we know we have a periodic function, we figure out what are the sine and what are the cosine coefficients. And a lot of that's going to come down to the symmetry of the function. So if the function happens to be even, then what that means is that f of theta is equal to f of minus theta. And so then it must look like a cosine function. So we have all the b sub n terms going to 0. And if it's odd, then you have f of theta equals minus f of minus theta, which sounds a lot like a sine function, so all of the cosine terms go to 0. And then you can go whether or not it's even or odd around pi over 2, and that's going to determine whether or not you're going to have even or odd coefficients even within the ends. So like, let's say we have even about pi over 2, then you have f of pi over 2 plus theta equals f of pi over 2 minus theta. And so you're going to have a 2n plus 1 equals 0. And you've got b sub n equals 0. So you have only cosine values with even n. All right. And also another thing you can do with this is you can generalize using x equals theta L over 2 pi, and that means that you have a period of L. And in doing that, you basically are going to substitute your theta coefficient for an x coefficient, which basically is going to be the same thing. And then, of course, there's the complex form, where you have f of x is equal to the sum from n equals minus infinity to infinity of a sub n e to the 2 pi I n x over L. And a sub n equals 1 over L, integral from 0 to L, f of x e to the minus 2 pi I n x over L dx. And so this is basically the same thing, but the only difference is that when you're using a complex form, you really don't care about the symmetry anymore, and you're really not taking advantage of the symmetry. When you're doing the sines and cosines, you can assume, the big advantage there is that if it's even, then you could just set all the sine terms to 0, and your symmetry automatically falls out of the problem just by taking into account only cosine terms. If it's odd, then you can only do the same thing with sine terms. When you're using the exponential, it's basically assuming that there is no relevant symmetry in the problem. And now all of your, everything is just integrated with respect to this exponential, and there is no overriding symmetry. Okay. It still works because, as you know, these exponential terms could break down into sine plus I, or cosine plus I sine, so you're still getting all the terms, and it's just a matter of what coefficients pop out.
Will you care on the test which one we use if we were to expand something as a Fourier series? Just pick one and go for it?
Just go for it. Yeah. I mean, unless I explicitly say that this thing has odd symmetry or something like that. If I don't make a statement about the symmetry, then have at it. However you want to do it. Okay, now this brings us to the Fourier transforms. Now, Fourier transforms, these are particularly fun because the basic idea here is that you take your Fourier series and you can expand it out so that you have something like f of x is equal to 1 over 2 pi times the integral from minus infinity to infinity of g of y e to the I xy dy, and g of y is equal to the integral from minus infinity to infinity of f of x e to the minus I xy dx. So this is known as a Fourier transform and an inverse transform. And then also you have the delta function defined, x minus x prime, where this is equal to the integral from minus infinity to infinity of 1 over 2 pi e to the I x minus x prime y dy. And if you integrate from minus infinity to infinity of this delta function, you're going to get either 1 or 0. 1 for x equal to x prime, and 0 for x not equal to x prime. So what happens is we're going to end up with something like this, where it's going to specify whether or not, you're going to have this function which you can kind of plug in, and it gives you a 1 or a 0, which is pretty handy. So the basic idea here is that you can transform from x, a function of x to a function of y, and these two functions are effectively equivalent to each other. And the only challenge in doing this is being able to solve the integral, which is why we spend a week on integration and all this other stuff on integration. So a lot of the problems that you're going to get involving this are just going to be effectively solving the integral or being able to do a Fourier transform of a particular function, which is what you see on last year's exam. And you'll notice here that the only real difference is that you have the 1 over 2 pi for the f of x, and there's nothing for the g of y. Oh, I should also note that while most of the formulas you're going to need are going to be in the Shalom's outline, or they're going to be fairly simple formulas, if there's a formula you think you need during the exam, let me know, and I could write it on the board for everybody to use. Okay. All right. Not that I don't think you're going to need anything, but just in case. Now, the neat thing about these Fourier transforms is that both the f of x and the g of y have the same symmetry, and because of that, you can actually do Fourier sine and cosine transforms in order to transform between them, because if, for example, if f of x is even, then g of y is going to be even, and you could transform from f of x to g of y using cosine, and vice versa. So you would just replace the e to the I xy with the cosine xy, and you got your transform. Or sorry, if you integrate just from 0 to infinity, you just put a factor of 2 in there. All right, and obviously it works the same way if you do the inverse transform. Now, another thing we did was we talked about 3D Fourier transforms. And the idea here is that when you do your transform, you're not just integrating across one dimension, you're actually integrating over an entire volume. And so you have f of a position x, and then you have e to the minus I k dot x. And then for the inverse transform, you're integrating over a volume in k space. And so you have a factor of 2 pi cubed in the denominator. And you have phi of k e to the I k dot x. So in this case, when you're solving your integral, you have this, you're going to use this whole use of symmetry thing. And so you have k dot x, where you're going to assume k is pointing along the z-axis, and so this whole integral works out a little bit better. And you can also have a delta function that you could define as a 3D delta function just by integrating the exponential term. So this is a lot of where this whole use of symmetry comes up in the integrals. And like I said, the only thing really challenging with the Fourier transforms is really just in solving the integral. That's why I kind of combine that. And then we talked a little bit about other integrals transforms. We talked about using the Heaviside function and Laplace transforms, and Fourier-Bessel transforms, and Hankel transforms, and Mellon transforms. And the basic idea of all these transforms is that if you take some kind of function, special function, or some kind of function which obeys certain boundary conditions, you can use it to transform between one space and another space. That's the whole idea of that. And what you'll see in more advanced physics is that depending on what boundary conditions your problem has, you can use these transforms in order to transform into something else that you can solve a little easier. Now, we're going to see Fourier transforms again in the future, particularly when we get to like partial differential equations, because we'll see that sometimes you can actually use this Fourier transform to solve a differential equation much easier than you can by actually working out any other way. And we'll use that for solving for eigenvalues or Green functions and things like that in the future. So that's just sort of a preview of what's coming up after the midterm. Yeah, like if you're trying to find, like for electrodynamics, you're trying to find a scalar potential, or you're trying to, I mean, that's a good example of it, really. If you're trying to find like just a scalar potential for a point particle in electrodynamics, then you need to solve for a Green's function for that. And what I found is in some cases like that, using the Fourier transform actually works a ton better than any other way to solve for that. And then once you've found that Green's function that helps you solve the differential equation, which helps you solve the problem. So the reason why we cover so many topics in here is because I'd say all of them are related, and you know, one day when I could sit down and do it, I'll figure out one problem which will probably combine every single thing you learn in this class. It'll be ugly, but you could probably put all that into one problem. All right. So the last thing we need to do, is there any other questions over Fourier transforms? No. Now we get to complex variables. And so with the complex variables, I mean, we talked about complex numbers. And these are things that you've seen and you've worked with before, you should have seen a lot. We talked about complex variables. Where a complex number could be something like z equals x plus iy, where x is the real part, y is the imaginary part, so we call this complex. And I, by the way, is equal to square root of -1. The complex variable would be something like you have a variable which depends on z, and it's made up of a real part, u, of x and y, and an imaginary part, v, which is made up of x and y. And so you get this whole new dynamics because of the fact that you have real and imaginary and they're all mixed in together. So this led us to the idea of the Cauchy-Riemann conditions, which is something that you know, you really should have memorized at some point, whether you want to or not, because you know, because they just keep popping up a lot when you're talking about complex variables. And the basic idea is that if the Cauchy-Riemann conditions are satisfied, then you have a derivative that exists at that point. If they're not satisfied, then you don't have a derivative at that point. And the Cauchy-Riemann conditions are partial u partial x is equal to partial v partial y, and partial u partial y is equal to minus partial v partial x. And so if you satisfy these conditions, then you have a derivative that exists, and you say you have an analytic function. So you need to be able to take these and you apply it as a test to any complex variable to see if it happens to be analytic or not. Now, where this is useful at is because we find that from contour integration, and contour integration basically means that if you're integrating, and this is the complex plane, so this is the imaginary axis, and this is the real axis. If you're integrating this a circle in this plane, and it's going from minus infinity to plus infinity, and there is a singularity inside of this complex plane, and a singularity is basically a point where the Cauchy-Riemann conditions are not satisfied, then you get 2 pi I times the sum of the number of singularities. Effectively. So this is really going to be given by the function that if we have, well, f of z naught, where z naught is a point of the singularity, is equal to 1 over 2 pi I times the integral over the closed contour of f of z divided by z minus z naught dz. That's the simplest way to write it. And so basically what all we're saying there is that all you have to do is just find out where these singularities are, and then everywhere there's a singularity, you gotta get rid of that part with the singularity. You know, give f, which is the analytic function at that point, that value, and then multiply by 2 pi I. And by doing that, you're solving your integral. The tricky part there is that you need to be able to evaluate exactly what that means for different functions and how the singularity fits in. Are you only going over half the singularity or a quarter of the singularity? Do you have 2 singularities in there that cancel out? Things like that. And that's kind of what you cover in your homework. So what you can do in general is you could say f, the nth derivative of f at z0 is equal to n factorial over 2 pi I times this integral, z minus z naught to the n plus 1 dz. So you can basically use this in order to calculate your integrals. And so anyway, that's the main takeaway that I have for the complex variables. So just really quickly going back, for the ODEs, I want you guys to be able to work through just a very systematic flowchart-like process of solving them, where you do, is it separable, is it exact, is there an integrating factor, assuming it's first order, first degree. And then can you make a substitution to make it separable? And then just kind of crank through this in order to solve for what the differential equation is. If it's second order and second degree or higher, then you do your initial guess of what the solutions would look like. Maybe, one other thing you can do is you can do a substitution in order to try to turn the second order or equation into a first order equation. But there's a lot more creativity that's sort of involved when you're talking about second order and higher. So you can do substitutions here too. So basically the differential equations, the reason why you need to know this is because pretty much everything you do in physics at this level is going to involve solving a differential equation. And so it's just the absolute most essential skill for any of these classes. Then for the infinite series, the big thing with the infinite series is going to be, can you take your infinite series and turn it into a function, and can you take your function and you turn it back into an infinite series? Because that way you can work with whatever it is you're working with as an infinite series or a function. It gives you more options for being able to solve your problem. Let's see. Oh yeah. Basically, the one on the midterm here, what I did was I said, well, I want you to integrate this function, but I want you to integrate it by using an infinite series. So I want you to actually turn it into an infinite series, integrate it, and then tell me what the solution is. You could solve this integral in different ways. I mean, there's other ways to solve the integral, but that's the way I want you to do it. You can check it in a different way, but that's. And so when I give you a problem like that and I say this is how I want you to solve it, that's when I want you to solve it that way. Okay? Even if there's an easier, better way to do it. So basically that's the whole challenge. You know, can you use the infinite series to do that? And in doing that, you know, the familiar series, you can use those. You can use geometric series. You can integrate or differentiate, however you want to do it. For evaluation of integrals, this basically comes down to two things. One, or three things. One is just changing the variables to something that you can find in the book or that you know the solution to. Another one is being able to differentiate or integrate with respect to parameters so that you can basically turn your integral into something that you know a solution to or that you can solve. And the third is the whole use of symmetry. And like I said, the whole reason we even cover this stuff is because the integrals are going to be useful for things like the Fourier series and transforms. And the Fourier series, that links back to what we talked about infinite series because, you know, they kind of go full circle there, where the big value of the Fourier series is that you can expand a periodic solution out in terms of sines and cosines, which might be easier to deal with, just like an infinite series. But then also, we have our Fourier transforms, which can be useful for things like data analysis, or we could use them for things like, you know, and really understanding our data. But you can also later on, you can see, you could use these to solve partial differential equations. So there's a lot of things I want you to use for this, but the real takeaway with this is that you'll probably get a Fourier transform problem, and the biggest challenge of that is going to be the integration part. And then for the 3D transforms is where your use of symmetry comes in. Now for complex variables, like I said, the whole idea here is going to come down to understanding the Cauchy-Riemann conditions and being able to test if something's analytic or not, and being able to do contour integration. And so there's a lot of equations that are worked out in Shalom's outlines, like integrals, definite integrals, where they could be solved using contour integration. So if I pick one out of there and I say, well, I want you to solve this integral using contour integration, then, you know, even though you see the answers right there in Shalom's outline, you should still be able to know how to use the contour integration to come up with that answer. Explain why it is, you know, why it is equal to pi over 2 or something like that. Okay. All right. Any questions? I think that was it. Page 8 was the last one.
For the contours, the main idea in that, we can just, if we set those limits, it's typically, like if it was a whole circle, it'd just be 0 to 2 pi r. Because we basically say that that singularity is an area of
0.
Okay.
Yeah, I mean, you could treat the singularity like a point. So what you're really doing here is, you know, there was that one way that we did it within the notes where you could take, like you say, 1 over z dz. Well, if z is equal to r e to the I theta, and dz is equal to r ir e to the I theta d theta, then this integral over a closed contour is just going to be equal to, let's see, the integral from 0 to 2 pi of 1 over r e to the I theta, I r e to the I theta d theta. And then basically everything cancels out except for the I, and then you have integral from 0 to pi of I d theta, which is just 2 pi I. So the whole idea is that you're only integrating around the singularity, and it doesn't matter how small I make this r, it's still going to give me the same answer. Because everything outside of the singularity is just empty space. And it doesn't contribute anything to the integral. And so the whole challenge to the contour integration is to see everything in this complex plane, where you integrate this whole thing, but this is the only thing that matters, which seems kind of odd, but that's kind of what it falls down to. And also, instead of integrating along a path or a straight line, we're integrating around a loop, which is a little bit weird, but that's what we get. Okay. Other questions? All right, well, if that's it, then I guess you guys get out a little early, and I will see you guys on Thursday. Like I said, we're going to be going over any other questions you guys have in preparation for the midterm, and particularly anything that you guys have on the homework. This will be your last chance to ask questions before it's due.